I always thought a spring composed of several steel plates. Until I studied the principle of leaf spring in depth, I realized that my previous idea was completely wrong. Come and see. When the truck is empty, it is hard, but soft when it's loaded. How does this happen? In fact, leaf spring is not a whole spring, but a lot of flat and curved steel plates, which are stacked layer by layer. The largest and longest one on top is called the main leaf. It is the core of the entire structure. There are two round holes at each end of the main leaf, called spring eye. It is through these two holes the leaf spring can pass through the fishing bait and rubber bushing to firmly fix it to the frame. Under the main leaf, there are layers of shorter steel plates, also called gradient pieces. The shorter they are, the lower they are. This design is not to save materials, but to make the spring more evenly stressed, to avoid concentrating the force on a certain steel plate and be directly broken. The center of all steel plates will be clamped together with center bolts or U-bolts to firmly clamp the entire leaf spring and axle together. The purpose is to make them work as a whole, instead of moving independently. But the real power of leaf springs is more than that. It also has a very important friction damping ability. When the car passes over potholes or bumps at high speed, these steel plates will rub against each other, which directly wears off some of the shock energy. This is like having a built-in shock absorber. To prevent the steel plates from running and misaligning, engineers will add steel clips to the side to firmly restrict them together. And between the leaf spring and the frame, a rubber bushing is added from the original heart-to-heart into a relatively soft connection to reduce noise and jolts. Now please imagine a picture. You are sitting in a fully loaded truck with a fast speed. A pothole suddenly appears in front of you, and the tire is suddenly pressed in. The impact force will instantly pass from the tire to the axle, and then all the force is transmitted to the leaf spring. Then the leaf spring starts to bend. This bending, which stores the huge shock energy, then the spring starts to slowly rebound and return to its original curvature. In this process, there are actually two forces working quietly. One is elasticity, which is responsible for holding up the body. The second is the friction between the steel plates, which is responsible for consuming the excess energy. So you won't feel the frame being suddenly lifted up, and the body will not shake violently. You will only feel a bumpy ride. However, aren't there spiral springs and air suspensions now? Why are leaf springs still used today? This is because of the trust in leaf springs, which cannot be replaced by modern suspensions. Although leaf springs are extremely simple in structure, but it is not afraid of mud, heavy loads, and impact. Its maintenance cost is low. More importantly, it is both a spring and a connecting rod, but also can directly position the axle. So you will find that trucks, tractors, and large off-road vehicles still widely use leaf springs to this day. Whether it's a bad road, a construction site, or a rural road, as long as it pulls heavy loads, leaf springs are the most stable choice. But now many are multi-axle trucks. How do leaf springs evenly distribute the weight? A multi-axle truck has not just one axle, but two or even three rear axles. At this time, leaf springs alone are not enough, but also a crankshaft and connecting rod mechanism. Its function is to share the weight among multiple rear axles. Let's take a 3-axle truck as an example. There is a steering axle in front and two rear axles. The distance between the two rear axles is less than 2 meters. We call them tandem axles. Assume the whole vehicle weighs 25 tons, the front axle weighs 5 tons, and the two rear axles share 20 tons. What would happen if there were no connecting rods? When the rear axle in front hits the speed bump, it will move upward. The second rear axle is likely to be lifted up, causing the tires to briefly leave the ground. This moment, all the weight will be on the first rear axle, which is very dangerous for a fully loaded truck. Engineers added a set of crank linkages. The two cranks rotate around point A on the frame. The leaf spring hanger of the first rear axle is connected to the first crank. The second rear axle's hanger is connected to the second crank. A connecting rod is used to connect the two cranks. In this way, when the first rear axle moves upward, it will push the first crank to rotate. The rotation is transmitted to the second crank through the link. The second crank immediately presses down on the second rear axle. The result is that one bridge rises, and the other bridge is actively pressed to the ground. Both tires always touch the ground. The load is automatically distributed on the two axles. So these seemingly bulky and primitive structures behind are all the stability gained from decades of engineering experience. This is also the reason why can still stay under the truck chassis,